Hi, everybody. Here is possibly the last video solution of the semester. This is section 6.1, exercise 13. Suppose that we have two inner products. I'll call them bracket sub 1 and bracket sub 2. Two inner products on a vector space V. Prove that the function defined as the sum of those two inner products is another inner product on V. All right, so in order to prove this, what we need to do is first understand exactly what's being said. What is it that we need to prove? The idea here is that this is not an equation that we're trying to prove or show or anything. It's a definition. This is a single noun. There is a function, this guy, with two inputs, a first input and a second input, and it is defined as a sum of two other functions, each with a first input and a second input. So what it means to take the inner product of two vectors, say x and y, well, I shouldn't say inner product yet because we don't know yet that this is an inner product. What we know is that it's a function. It's defined as, well, we take that first entry and that second entry, and we put them in as the first and second entry in bracket sub 1, which we know is an inner product. And then we put that first entry and that second entry as the first and second entry into bracket 2, which we know is an inner product. And then we add those two things together. So this is a scalar from the field. That's what an inner product does. It takes two vectors and combines them in some way according to some formula to give you a scalar. So then this is also a scalar, and this is addition of scalars, addition in the field. So that means that this function now has combined two vectors x and y and assigned an element from the field, a scalar. Great. So that is what this function is doing. Let's undo that to give ourselves some space to work with. So what we want to prove is that the function defined in that way is another inner product on V. All right, so we need to prove that that thing is an inner product. So we have to use the definition of an inner product. An inner product is a function that takes two vectors and combines them to give you a field element, satisfying several conditions. So let's prove that those four conditions hold for this function. So the first condition is that for any three vectors, x, y, and z in the vector space, it's supposed to be that if you combine the sum of x and z with y, you get the same thing as if you were to combine x with y and then combine z with y and then add those up. So that's what we want to show, is that if we use this function, this bracket with no subscripts, on a sum and another vector, we get the same thing as if we use that function on the vector x with the second vector y and the vector z with the vector y, and then we add those results together. So let's prove this. Let's start with the thing on the left. Well, the thing on the left is x plus z comma y. And now let's use the definition of this function. Well, by definition, the function just uses the two actual inner products. So I'm going to use the inner product with subscript 1. I'm going to take the first entry, x plus z, and use it as the first entry of the inner product. And then the second entry, and I'll use that as the second entry of the inner product. And then I'm going to do the same thing with the inner product subscript 2. That is, I'm going to take the first input into this function, the brackets with no subscript, and I'm going to use that as the first entry. And I'm going to take that second entry into our brackets with no subscript, and I will use that as the second entry in brackets sub 2. Right, so all this is doing, this is not using anything about inner products. This is just the definition of the function that we're trying to prove something about. But now we know that bracket sub 1 and bracket sub 2, those actually are inner products. So in particular, they satisfy condition 1. They satisfy something like that equation up there. So that means that we could rewrite this x plus z comma y using the inner product sub 1 as x together with y sub 1 plus z together with y sub 1. And similarly, bracket sub 2 is an inner product. So that thing on the previous line is the same as x combined with y using this inner product plus z combined with y using this inner product. So this is properties of inner products. These guys actually are inner products, so they have all the properties that inner products are supposed to have. Well, now that when you take the inner product of x and y using brackets 1, that's a field element. Similarly, that's a field element, that's a field element, and that's a field element. So all the things that we know about scalars hold. In particular, addition is commutative and associative. So I can rearrange using properties of fields. Well, specifically here, the field will be either real numbers or complex numbers. So really, when we're talking about inner products, you can actually be less general and say properties of numbers. Well, I can just rearrange and combine. I can say that this is the same as the inner product of x with y using brackets 1 plus the inner product of x with y using bracket 2. And then I'm going to add to that the inner product of z with y using brackets 1 plus the inner product of z with y using bracket 2. Again, all I'm doing is taking these 4 numbers that are being added together, rearranging how they're written, and grouping them, because now the thing in the parentheses here on the left is exactly, again, by the definition of our function. That's just bracket x with y with no subscript, and this is the right parenthesis. That's the same as bracket z with y with no subscript. But that's exactly what we wanted to show, that if we use this bracket with a sum on the left and a vector on the right, it was the same as a sum of brackets, the first sum end on the left and the second entry on the right, and then the second sum end on the left and the same entry on the right. That's what we have. X plus z combined with y is the same as x combined with y plus z combined with y. So whatever this function is defined as a sum of 2 inner products, it satisfies the first condition of itself being an inner product. Let's do maybe one more of these to get a feel for exactly how we'll prove this. Condition B of being an inner product is that for all x and y vectors in V, and for all C in the field, either real numbers or complex numbers, it's supposed to be that the combination of a scaled version of x with y results in the same thing as combining x with y and then multiplying that result by c. So that's the thing that we want to check. Again, let's start with the thing on the left. Suppose we have c times x and we want to combine it with y. Well, using the definition of our function. This is just cx combined with y bracket 1 plus cx combined with y using bracket 2. But now bracket sub 1 is an inner product and bracket sub 2 is an inner product. So using properties of inner products, specifically the second property, property B, we know that this thing on the left is in fact the same as C times the inner product of x with y using inner product 1, and this thing on the right is the same as C times the inner product x with y using inner product 2, and now these are numbers. So properties of numbers or fields, I can factor out a C from both of these numbers, both of these field elements. And now inside the parentheses, I see exactly again what the function bracket dot comma dot bracket means. So definition of our function says that this is the same as C times bracket x comma y, close bracket. And that then shows what we wanted to show, that if we start with cx comma y, we can show that that is the same as C times x comma y in the brackets. Okay. All right, so let's do C and D, the last two properties of an inner product, but I won't provide all the justifications along the equality as we go. Property C says that for all vectors x and y in the vector space, the inner product of x and y, if I take the conjugate of that, it's the same as if we did the inner product of y with x. So if our function is going to be an inner product, this condition needs to be satisfied. So again, let's start with the thing on the left. That is x comma y with the conjugate bar over the whole thing. Well, that's just x combined with y sub 1 plus x combined with y sub 2. And we have a conjugate bar over the entire thing. But now the conjugate of a sum is the sum of the conjugates. That's certainly true for real numbers where the conjugation doesn't do anything, but it's also true for complex numbers. So this is the sum of the conjugates of two complex numbers separately now. But by properties of the inner product, the conjugate of the inner product with x and y using inner product 1, well, that's the same as the non-conjugate of the inner product of y with x. Similarly, I can change the order of the x and the y in the second inner product, but I get to drop the conjugate, and now this is by definition again, bracket y comma x, which means that yes, I can change the order with the brackets without subscripts as long as I have a conjugate bar included. And finally, the last condition is that for all vectors x in the vector space, the inner product of x with itself is a real number that is greater than or greater than 0 if x is not the 0 vector. So we'll put question marks since that's the thing that we want to verify. And let's consider what happens if we use this function, but put the same vector in both slots. Well, by definition of the function, this is putting x in both the slots for the first inner product, and then putting x in both of the slots for the second inner product. And now, by definition of an inner product, we know that this thing is greater than 0 if x is non-zero, and that thing is greater than 0 if x is non-zero, and the sum of two real numbers that are greater than 0 each is also greater than 0 if x is not the 0 vector. So in particular then, well, 0 plus 0 is 0. So what we've really shown is that, yes, the combination of x with x using this bracket is strictly greater than 0 if x is not 0. So now we have shown all four of the properties that a function would need in order to qualify as an inner product. It respects addition in the first entry. It respects scalar multiplication in the second entry. It is conjugate commutative. That is, you can change the order, but you pay the price of taking a complex conjugate. And if you take the product of a vector with itself, you get a greater than 0 real number. Therefore, bracket dot comma dot bracket is an inner product on the vector space V. All right, hopefully that's helpful, and I will see you guys bright and early on Thursday.